The next topic we're going to discuss is called structural change. And structural change refers to a case where there has been a difference in the fundamental nature of the relationship between the estimation sample and the holdout sample. Okay. So far, we've been assuming that what was good for the estimation sample is probably going to be okay for the holdout sample too. So we estimate the parameters based on the estimation sample and apply the estimates on the holdout sample and measure the forecast accuracy. Okay. But if there has been a fundamental structural change in the relationship between the estimation sample and the holdout sample, then our accuracy results may not be very reliable. So this is possible when there has been a catastrophic incident that has fundamentally changed the relationship. For example, airline industry, after 9/11, there has been a sudden change. And suppose if in our analysis it so happens that the holdout sample actually is post 9/11 and the estimation sample is pre 9/11, then the estimate that we arrive at is not going to be valid for the holdout sample. Okay, of course 9/11 is a very dramatic example, but in the ordinary course of events, some things may have a dramatic effect on the holdout sample and the estimation sample relationship. For example, a new product comes in or new technology comes in that changes everything, or new competitor enters the market and that changes everything. So it is important for us to test and see whether there is a structural change that has occurred or not. Okay. If we can be sure that there has not been a structural change, then we will have more confidence in the accuracy measures that we develop with the holdout sample. So for this, what we're going to do is we're going to expand some more variables. So you have the Y column and then you have your X columns, the X range, right? So now we're going to include we're going to duplicate all of these X's, okay, with a holdout, with a variable called U. Okay, so here is how this is going to work. So our model for estimation sample, so if you have only estimation sample, then it is going to be that, okay, the regular regression model, beta sub 0, beta sub 1, X sub 1, and so on and on. And that is for time period t equal to 1 to n sub 1, that's our estimation sample. Now, n sub 1 plus 1 through the rest of the way, so this is our holdout sample. Okay. Now, suppose if there is a structural difference, now instead of beta sub 0, the holdout sample model is maybe gamma sub 0, and instead of beta sub 1, it is gamma sub 1, etc. Okay. So we can write this in a slightly different way by saying that gamma sub 0 is beta sub 0 plus a delta value, delta 0. Delta 0 can be positive or negative. And similarly, gamma sub 1, that is for the holdout sample, is going to be beta sub 1 plus a small change. Okay. Similarly for the rest of the variables. Okay. Now notice that if all of these deltas are 0, then the estimation model and the holdout model are going to be exactly the same. Okay. So our test that we have to perform, the hypothesis test, is to see whether all the deltas are 0 or not all the deltas are 0. Okay. At least one is different from 0. Okay. Here, if we do not reject the null hypothesis, then we are okay, because the estimation sample model and the holdout sample model are about the same. So our accuracy measures can be relied upon. But if any of the delta is different from 0, if we reject the null hypothesis, then all bets are off. So your holdout sample is not going to be very reliable, in which case you have to change. Okay, if that happens, then you have to change the sampling. You have to have a different set of estimation sample and holdout sample such that the holdout sample model will be the same as the estimation model. So this is more what we could do when we reject the null hypothesis is to go back and redo the sample. Okay, there is nothing else we could do if the models are different. Okay, so how are we going to test this? Okay, to test this, we're going to define two different models. Model 0 is just the regular model that we had previously. Okay, beta sub 0 and beta sub 1 through beta sub k. So this is like that. Okay, and we will apply this to the entire sample, 1 through n. Okay, then we define a second model where we have the original model, and then we take each of the deltas, okay, and multiply by a variable called u. And we will apply a value of 0 for u. It's the same u everywhere, you see. We will use 0 for the value of the column u for the estimation sample, and 1 for the holdout sample. Okay. And then we multiply the u with x sub 1, u with x sub 2, and so on, and we will have the delta. So if any delta is different, well, if all the deltas are 0, then there is no difference between model 0 and model 1. But if any one of the delta is different from 0, so then model 0 and model 1 are different. So now we have two different models, and we can test whether there is a difference in the two models by using the additional sum of squares test. Okay, so here are we will find the SSE for model 0, and the degrees of freedom will be n minus k minus 1 here, and we will apply we will compute SSE for the second model number 1. Okay, and the degrees of freedom will be n minus 2k minus 2. We're going to have a bunch of new variables here, and then the F statistic will be this. Okay, and then we can compute the p-value and see whether it is significant or not. Okay, so two different models, model 0, model 1, and we compute additional F value and then the p-value corresponding to that additional F statistic. So let's look at a numerical example of this procedure.